Welcome, BSCS 5th semester students. Today we're kicking off Chapter 1 of our course with this explainer. We're going to build a rock-solid foundation for computer networking, and we're doing it by taking a top-down approach. Instead of, getting instantly lost in the weeds of electrical signals and physics, we're actually going to start with the big picture, the internet, exactly as you use it every single day, and then we'll work our way down through the layers. Let's get right into it.
Okay, let's quickly look at our roadmap for today's session. Number 1. The Internet and Protocols. 2. Exploring the network edge. 3. Links and physical media. 4. Inside the network core. 5. Packet versus circuit switching. And finally, 6. The global ISP hierarchy. Let's kick things off with Section 1, the Internet and Protocols. Now, here is a super common student confusion I see all the time. A lot of people treat protocols as just, pieces of software or some programming language. But actually, scratch that, the absolutely crucial point here is that protocols are fundamental rules. They dictate the exact format, the specific order, and the precise actions for every single message sent and received among network entities. Think about it. If a server expects a highly specific code to open a connection, your computer better send exactly that code in exactly the right order or literally nothing happens.
A great way to bridge the gap here is by looking at human behavior versus computer behavior. Just like we humans have social protocols, like saying hi before asking someone what time is it, computers use network protocols. If a computer wants a file, it can't just magically grab it. It has to send a TCP connection request first. Then the server replies with a TCP connection response. Only after that strict handshake does the computer send a GET request for the file. The rules of engagement are rigorously defined.
Moving right along, let's hit Section 2. Exploring the network edge.
To actually get onto the internet, we rely on an access network. Two classic examples you're probably familiar with are DSL and cable. Now, what's really fascinating here is the core architectural difference between the two. DSL uses your existing telephone line, providing a dedicated connection straight to the central office's DSLM. Cable, on the flip side, uses a hybrid fiber coax network. This means homes share the access network to the cable head end. This is a practical, everyday networking reality. That shared medium, that is exactly why your table internet might suddenly slow down to a crawl at 8 p.m. when everyone in your neighborhood jumps online to stream HD video at the same time. Now for Section 3, links and physical media.
Because, data doesn't just travel by magic. Once it leaves your home router, it physically has to cross space. First up is standard twisted pair copper wire. This is what we call guided media, meaning the signal is physically contained right inside the cable. These two insulated copper wires form the absolute backbone of most local area networks. If you've ever snapped an Ethernet cable into a laptop, yep, that was likely twisted pair. And it's no slouch. Category 6 can easily push 10 gigabit per second speeds over short distances.
Next up is coaxial cable. Notice the concentric copper conductors. Coax is a real step up for certain applications because it gives us bidirectional broadband capabilities. Because of the way it's physically shielded, it allows multiple frequency channels to travel on a single cable at the exact same time without interfering with each other. We're talking hundreds of megabits per second per channel. But when we need the absolute highest speed point-to-point transmission across huge distances, we rely on fiber optic cables. Instead of shooting electrical signals over copper, fiber carries tiny pulses of light through glass fibers. Each pulse is a bit of data. They are mind-blowingly fast, handling tens to hundreds of gigabits per second. And the best part? Because they use light, they are entirely immune to electromagnetic noise. This right here is the heavy-lifting physical media of the internet core. Of course, not all media is guided. Unguided media, like wireless radio links, broadcast signals right through the electromagnetic spectrum. Now, these face real environmental challenges. Think signal reflection, getting blocked by thick walls, or just general interference. Yet, they power our modern mobile world. We use local Wi-Fi to cover tens of meters and 4G or 5G cellular to cover kilometers. We even use satellites for remote access. Though, keep in mind, geostationary satellites introduce a noticeable 270 millisecond end-to-end delay. Why? Because the signal literally has to travel to outer space and back.
All right, let's dive into Section 4, inside the network core.
Leaving the physical links and the edge behind, we are now in the core of the network. Listen up, because I guarantee this will be on your exam. You absolutely must know the difference between routing and forwarding. The crucial thing is understanding their scope. Think of it like taking a giant road trip. Routing is the global brain. It's like Google Maps running complex algorithms to calculate your entire path from New York all the way to Los Angeles.
Forwarding, which is also known as switching, is the local, split-second action at a single intersection. It's the moment a router looks at a packet's header, checks its local table, and physically moves that packet from the input link to the correct output link. So remember, routing makes the map, but forwarding takes the step.
Next up is Section 5, Packet versus Circuit Switching.
So, we have to compare the two fundamental ways data moves through this network core. Let's start with traditional telephone networks, which use circuit switching. In this model, before you even speak, a dedicated end-to-end circuit is reserved just for you. To share the physical wire, they use a technique called multiplexing. Now, frequency division multiplexing, or FDM, splits the total bandwidth into continuous narrow frequency bands, kind of like tuning into different radio stations. Time division multiplexing, or TDM, takes a different approach. It gives each user the full bandwidth, but only for exclusive, periodic, split-second time slots. But either way, in circuit switching, your network resources are strictly reserved, whether you're furiously sending data or just sitting there in total silence.
Okay, let's dive into a classic math problem step by step to mathematically prove why the internet relies on packet switching instead of circuit switching. Imagine a network link with a 1 gigabit per second capacity. That's 1,000 megabits. Let's say each user needs 100 megabits per second when they are actively downloading. Now, if we use circuit switching, we strictly reserve that 100 megabits per user. 1,000 divided by 100 means we can support exactly 10 users. That's it. User number 11, they get a busy signal. But wait! Users are usually only actively downloading about 10% of the time. Most of the time, they're just reading a web page or staring at a screen. Packet switching doesn't reserve resources. It shares them purely on demand. Because of the laws of probability, if we allow 35 users onto this exact same network, the statistical chance that more than 10 users will transmit at the exact same millisecond is less than 0.0004. So using packet switching, we just supported more than 3 times the number of users on the exact same hardware. It's a massive efficiency gain.
While that math heavily favors packet switching for dealing with bursty internet traffic, we are engineers, so we have to acknowledge the trade-offs. Because we don't reserve circuits, what happens if, by some total fluke, 15 users actually do try to send massive files all at once? Well, the router's memory buffer fills up. This introduces the very real risk of excessive congestion. Packets will experience queuing delays as they wait in line, and if that buffer overflows, packets will literally be dropped and lost forever. Therefore, packet switch networks absolutely rely on complex upper-layer protocols to provide reliable data transfer and to manage that congestion.
And finally, Section 6, the Global ISP Hierarchy.
Let's zoom all the way out and think about the sheer logistics of the internet. There are millions of local access ISPs in the world. If we tried to connect everyone directly to everyone else, it just wouldn't scale. It would require an impossible O of n squared number of physical cables. On the other hand, if we just had one massive global ISP monopoly connecting everyone, it would instantly invite competition, and new global ISPs would just pop up anyway. So how is the actual real-world internet structured to handle this?
To solve this massive scaling problem, the internet evolved into a network of networks, a layered hierarchy. Your home or mobile network connects to an access ISP. Those, in turn, connect to regional ISPs. To get across the country or, say, across an ocean, those regional ISPs pay Tier 1 ISPs. These are the massive global transit networks. And to save money on paying those Tier 1 providers, competitor networks will actually connect directly to each other at physical locations called Internet Exchange Points, or IXPs. Furthermore, massive tech giants like Google have built their own private content provider networks. They lay their own global fiber optics to bypass Tier 1 providers entirely, bringing their services as close to you as possible.
And that covers the big picture of Chapter 1. As you review this material for our next class, I want to leave you with this foundational engineering question. Knowing that the internet uses packet switching, complete with its inherent risks of delay and packet loss, how do we engineer protocols on top of it to provide the ironclad, reliable guarantees of circuit switching? Really think about that, because trying to make totally unpredictable packet networks behave perfectly, that is the core problem that will drive so much of our learning for the rest of the semester. See you in the next Explain.